A black horizon swallows the last starlight. The heavens, once strewn with fire, are cold and silent. The narrator's voice emerges over an endless expanse of dark. There will come a night when no star will shine. No sun, no moon, no glow. Of galaxies, only the quiet breathing of a universe grown old. This is not myth, nor prophecy, but the eventual consequence of physics itself. Every star will burn its fuel. Every light will fade. Time will stretch on, far beyond the lifespans of worlds and civilizations, until even the memory of light becomes an echo in the black. The path to this starless tomorrow is already written in the laws of thermodynamics, nuclear fusion, and cosmic expansion. And yet, hidden in the details of this journey are possibilities as wondrous as they are terrifying, strange future stars. Born in the ashes of the old, rogue worlds, wandering the dark and exotic matter, reshaping the fate of time itself. Somewhere along that path, the universe will decide whether darkness is its final state, or merely the beginning of something stranger. Long before the language of science, the sky was a mirror for human thought. To the ancient Babylonians, the constellations were more than patterns of light. They were a calendar, a clock, a map of divine intention. They etched the positions of stars into clay tablets, recording the slow dance of the heavens as faithfully as one might record the growth of a child. In Greece, Aristotle pondered the lights above as eternal and unchanging, perfect spheres of fire moving upon crystalline shells. The stars, he believed, were fixed in their number and form, immune to the decay that claimed all things on earth. To think otherwise was to challenge the perfection of the cosmos itself. For millennia, this belief endured, that the night sky was constant, that the same stars which guided shepherds and sailors would shine forever. The flicker of starlight became a symbol of permanence. The first cracks in this illusion came not from philosophy, but from glass. In the early 17th century, Galileo Galilei lifted a small telescope to the heavens. Through its imperfect lenses, the sky changed. The Milky Way dissolved into uncountable points of light, far more than the naked eye could see. He found blemishes on the moon, moons around Jupiter, and phases of Venus that shattered the old models of celestial perfection. And yet, the stars themselves remained points, distant and unresolved. They still seemed immutable, their secret lives hidden by the limits of human vision. It would take another 2 centuries for light itself to reveal their nature. In the 19th century, Joseph von Fraunhofer turned a prism upon sunlight and saw a rainbow crossed with thin, dark lines, signatures of specific elements absorbing particular wavelengths. Soon, spectroscopy was turned on the stars. Each point of light carried a chemical fingerprint, a message from its surface across unimaginable distances. By this method, astronomers learned that the stars were not cold lights affixed to the firmament, but burning spheres, their light shaped by hydrogen, helium, and heavier elements forged in their cores. The constancy of the heavens gave way to a new picture. The stars were objects, made of matter, obeying the same physics that governed the Earth. That the true heartbeat of a star would not be revealed until the 20th century. Arthur Eddington, studying the sun's mass, luminosity, and temperature, proposed a daring solution to the mystery of its power. The sun, he argued, shone by fusing hydrogen into helium, releasing energy according to Einstein's equation E equals mc2 equals mc2 equals mc2. The furnace of the stars was nuclear, not chemical, and nuclear fires, unlike wood or coal, could burn for billions of years. Yet, even in this triumph of understanding, lay a shadow. If a star's energy came from finite fuel, then it could not shine forever. Its lifetime would be set by its mass, its temperature, and the rate at which it consumed its reserves. Cecilia Pangaposhkin, in a landmark 1925 thesis, proved that stars were composed primarily of hydrogen and helium, a revelation that confirmed Eddington's model and deepened the understanding of stellar lifespans. Hydrogen was abundant, but not infinite. The clock was already ticking. By mid-century, the theory of stellar evolution had emerged in detail. A star began as a protostar, collapsing from a cloud of dust and gas, igniting when pressure and temperature became high enough to start fusion. In the main sequence stage, where the Sun now resides, it spent most of its life in a steady balance between gravity's inward pull and the outward push of nuclear energy. But that balance was temporary. Once the core hydrogen was exhausted, gravity would tighten its grip. The star would swell into a red giant, shedding layers into space. For small and medium stars, this path ended quietly, with the core cooling into a white dwarf, a faint ember that would radiate its heat for billions, even trillions of years before fading to black. Massive stars followed a more violent script. Their cores collapsed in titanic supernova explosions, leaving behind neutron stars or black holes, remnants so dense they warped space itself. The Hertzsprung-Russell diagram, a chart plotting stars by their brightness and color, became a kind of family portrait for stellar life. It showed not only where a star was in its life cycle, but where it was headed. It was a revelation. The night sky was not static at all, but a theater of births, lives, and deaths on timescales, too vast for any human eye to witness in full. And here, quietly, came the first recognition of an idea both unsettling and profound. Every star in the sky, from the faintest red dwarf to the brightest blue giant, was temporary. Their lives might span millions, billions, or in the smallest stars, trillions of years, but not eternity. Even the slowest burning would one day exhaust their fuel, cooling into darkness. The seeds of a starless universe were already sown in this understanding. For if every star has a lifespan, and if no new stars can form forever, then there must come a time when the last one shines its final light dot in the ancient world. The constellations were thought to be eternal guides. Now, science had revealed them as momentary configurations, the brief overlap of countless stellar journeys. Even the stars of Orion, fixed in human memory for tens of thousands of years, would one day drift apart, their members burning out or moving on, leaving only emptiness where a hunter once strode. The night sky was no longer a symbol of permanence. It was a living record of change, a snapshot in a story that began before humanity and will continue long after. And yet, this was only the first step toward the realization that the universe itself was headed toward darkness. The recognition that stars die raised a deeper question. What happens when not just one star, not just one cluster, but all of them are gone? That question would lead science into territory both awe-inspiring and unsettling, a journey into the deep future toward the shadowed horizon of a cosmos without light. The revelation came not as a single moment, but as a slow dawning, like the first light of morning creeping across a vast and ancient landscape. It began with a truth so simple it could be written in a sentence. Every star has a fuel supply, and that fuel will one day run out. For centuries, the stars had seemed immune to decay, steadfast against the erosion that claimed all things on Earth. But the understanding of nuclear fusion changed that. Fusion was a process with a beginning and an end. It transformed hydrogen into helium, releasing light and heat, and in doing so, it slowly, inexorably exhausted the very source of its own power. A star's life is determined by a delicate balance between gravity's inward pull and the outward push of radiation from fusion. But this balance is not eternal. It is only a temporary truce. The length of that truce depends on mass. The most massive stars, brilliant blue giants, live fast and die young, their prodigious luminosity burning through their hydrogen. In mere millions of years, they are cosmic fireworks, dazzling but brief. Smaller stars, like our sun, measure their lives in billions of years. The tiniest red dwarfs, glowing faintly in the cold reaches of galaxies, can endure for trillions. Longer than the universe has yet existed. Yet no matter the pace, the end is the same. Fusion stops. Gravity wins. The shock deepened with the recognition that this was not merely the fate of individual stars, but of all stars. Even the longest lived could not shine forever. And when the last one burns out, the cosmos will have no source of new light. Here the second law of thermodynamics enters, patient and unstoppable. Entropy, the measure of disorder, always rises. The universe moves toward equilibrium, toward a state in which energy is evenly spread and no work can be done. Stars fight entropy by concentrating energy in their blazing cores and radiating it outward. But they can only fight so long. In the far future, the great engines of fusion will fall silent. White dwarfs will cool to black dwarfs. Neutron stars will fade. Black holes will be the last strongholds of energy, and even they will eventually evaporate through Hawking radiation. This is the heat death, not an explosion, not a collapse, but a quiet surrender to uniformity. A cosmos without temperature differences, without the gradients that drive motion, light, and life. The scale of this truth was overwhelming. Human history spans only thousands of years. Civilization itself has seen barely a few hundred generations. The Earth has orbited the Sun less than 5 billion times, a blink in cosmic time. Against the lifespan of stars, human existence is smaller than the flutter of a single moth's wing against the age of a forest. And yet, the universe's future is vaster still. The death of the first generation of stars has already come and gone. The death of the last will be trillions of years away. These numbers stretch beyond human comprehension, not just long, but different from the timescales of life, thought, and memory. The final blow to the illusion of a permanent night sky came from the expanding universe itself. In the 1920s, Edwin Hubble's measurements revealed that galaxies are receding from one another. Space is not static, it is stretching, and that stretching does not slow. In fact, it is accelerating, driven by the mysterious force called dark energy. The consequence is profound. As galaxies drift apart, the supply of interstellar gas from which new stars are born will be trapped within each galaxy, cut off from the rest. Within each isolated island of stars, the fuel will dwindle. Star formation will slow, then cease. The great spiral arms of galaxies will fade, leaving only small clusters of aging suns, separated by gulfs of blackness, beyond a certain point in the far future. Distant galaxies will slip beyond the cosmic horizon, receding faster than light. Due to the expansion of space itself, the universe will grow not only darker, but lonelier. Observers, if any remain, will see only the dim remnants of their own galaxy, adrift in a silent ocean by the end of this process. the interstellar medium will be spent. No more clouds of gas will collapse into new suns. No more stellar nurseries will bloom with light. Galaxies will become graveyards of burned-out stars, their beauty erased not by catastrophe, but by the slow arithmetic of time. And so the shock was complete. The universe is not a perpetual machine, not a grand clock that will tick forever. It is a story with an ending already written into its opening lines. This was not the end of curiosity, far from it. Instead, it was a call to look further, to ask how such an ending unfolds in detail, to trace the path from this moment of abundant light to the final, starless tomorrow. The next step would not only measure the coming darkness, it would reveal the strange and exotic forms the universe will pass through along the way. To follow the path toward a starless tomorrow, science had to do more than accept the fate of stars. It had to chart it. No one alive could witness the death of a galaxy or the final flicker of a long-lived red dwarf. The journey into the deep future would be made not by waiting, but by observing the present with enough precision to read its hidden timelines. In the archives of the night sky, there are already galaxies far older than our own. Their faint, reddish light carries the memory of an age when the first stars were already dying. Some of these ancient systems are compact and quiescent, their star formation long since quenched, their remaining suns drifting through quiet darkness. They are, in a sense, previews of our own galaxy's future, globular clusters to serve as living fossils. These dense swarms of stars orbit the Milky Way's halo, many more than 10 billion years old. Their color magnitude diagrams, cousins to the Hertzsprung-Russell plot, show a population in late Middle Age, with most massive stars already gone. They are reminders that even the brightest patterns fade, and that the night sky is a work always in progress, never in stasis. The theoretical map of the future begins with what we know of stellar lifespans. Massive, short-lived blue stars have already vanished from many ancient galaxies, leaving behind neutron stars, black holes, and heavy elements scattered in interstellar clouds. Yellow stars, like our sun, will follow in billions of years, swelling into red giants before shrinking to white dwarfs. These white dwarfs are the embers of the cosmos. They no longer fuse atoms. They shine only from the stored heat of their collapse. Over time, immense spans far beyond the age of the current universe, they will cool and fade, becoming black dwarfs, dark, cold, remnants invisible to any telescope. No such object exists yet. The universe is simply not old enough to have produced one, but the physics that predicts them is clear and relentless. Some of the most extreme predictions arise when we extend this vision beyond ordinary matter. If protons are not perfectly stable, as some grand unified theories suggest, then even black dwarfs will eventually decay into lighter particles, erasing the last macroscopic structures of normal matter. This process would take at least 103 for 103 for 103 for years, perhaps much longer, but in a universe measured by trillions upon trillions of years, such limits are within reach. Simulations of the degenerate era, the epoch. After all, normal stars have burned out. Predict a universe lit only by the occasional flare of extraordinary events, collisions of brown dwarfs, mergers of dead stars, or the feeding of black holes. These flashes will be rare, separated by millions of years of darkness. Black holes themselves will define the next chapter of the cosmos. Born from the collapse of massive stars or the mergers of smaller remnants, they will be the last significant concentrations of matter and energy. In the short term, meaning billions to trillions of years, they will dominate the gravitational architecture of galaxies, swallowing stray stars, planets, and gas. But even they are not eternal. Stephen Hawking's theory of black hole radiation predicts that over vast timescales, they will lose mass as they emit faint thermal radiation into space. A black hole of stellar mass will take 106,710, 671,067 years to evaporate. The giants at galactic centers will last far longer, up to 101, 001, 0100, 101, 00 years. When they finally vanish, they will go not with an explosion, but with a fading whisper of light. Astronomy cannot watch such spans unfold directly, but it can look both backward and outward to find patterns that mirror what is to come. The cosmic microwave background, the afterglow of the Big Bang, is one such pattern. It shows a universe once hot and dense, now cold and stretched thin by expansion. By tracing this cooling trend forward, scientists can project the temperature decline into the far future, to a point where the average energy of the universe is near absolute zero. The James Webb Space Telescope offers another form of time travel. By capturing the faint light of the first galaxies, it shows the conditions from which all later stars emerged. In the early universe, gas was abundant and star formation furious. Over time, that gas has been steadily locked away in stars, planets, and compact remnants. Observing galaxies at different ages reveals the slow decline of star formation, a trajectory pointing toward a future with none at all. Closer to home, supercomputer simulations extend these trends to unimaginable horizons. These models take the physics of gravity, thermodynamics, and nuclear fusion, then run them forward for trillions of years. They show the spiral arms of galaxies fading, the scattering of stars as gravitational encounters nudge them into intergalactic space, the collapse of star clusters into dense, dark cores. In these simulations, the Milky Way's fate is sealed long before the last star goes out. In about 4 billion years, it will merge with the Andromeda Galaxy, forming a massive elliptical galaxy. This new structure will have a burst of star formation, briefly delaying the inevitable, but even that new generation will burn out in time. The merger will leave behind a swollen galaxy filled mostly with old stars, white dwarfs, neutron stars, and black holes. The investigation of this deep future is not only a question of astrophysics, but of cosmology. The expansion of the universe ensures that, over time, even light from our nearest galactic neighbors will be stretched beyond detectability. In the distant future, observers within what remains of the Milky Way Andromeda remnant will see nothing beyond their own galaxy. The larger universe will be hidden, not because it has ceased to exist, but because the expansion of space has carried it beyond the reach of sight. It is a profound thought in such a future. Even the memory of a universe filled with galaxies will be lost to direct observation. The night sky, once alive with 100 billion suns, will become an empty canvas. There are subtler questions, too, about the possible role of dark matter in the long future, about whether dark energy is truly constant or might change over time. If dark energy grows stronger, it could tear apart galaxies, stars, and eventually even atoms in a big rip. If it weakens or reverses, the universe could collapse in a big crunch. These possibilities remain open, their likelihoods resting on measurements still being refined today. For now, the prevailing models suggest a slow fading rather than a violent end. But within that slow fading lies the most haunting truth. The age of light is temporary, and we live in its brief central act. In studying the deep future, science confronts not only the limits of its instruments, but the limits of human imagination. Time on such scales erases familiar reference points. Civilizations will rise and fall in the space between two stars' deaths. Species will emerge and vanish before a single white dwarf cools appreciably. And yet, for all its remoteness, this knowledge has weight in the present. It tells us that the universe is not a fixed, eternal stage, but a changing, aging structure, and that the darkness we see between the stars is not empty space, but a glimpse of what will one day fill the whole sky. From here, the path into the future grows stranger. The physics of the present can project the decline of light, but the later eras, the age of black holes, the age of darkness, challenge the boundaries of what we can model. And within those shadows lie the most unsettling possibilities of all, that the universe's dark future may hold surprises as radical as the bright beginning we once called the Big Bang. If the present age is the age of light, then what follows is its long twilight, a cosmic slow-motion descent into shadow. The end of starlight will not come suddenly. It will fade in stages, each stranger and more alien than the one before. The first great transformation will begin when the last stars of the main sequence exhaust their fuel. Red dwarfs, the smallest and longest lived, will be the final holdouts. Their cool, dim light will endure for trillions of years, far beyond the life expectancy of suns like ours. In the early degenerate era, the universe will be lit only by these stubborn embers. Their glow will be faint, reddish, and scattered thinly across a sky already emptied of most familiar constellations. Even these survivors will eventually fade. As they do, the universe will become a place without fusion, without the birth of new light. What remains will be the corpses of stars, white dwarfs slowly cooling into black dwarfs, neutron stars spinning ever more slowly in the dark, and black holes holding their silent dominion over the gravitational landscape. In this age, light will be rare but not absent. Gravitational encounters could occasionally send dead stars or brown dwarfs colliding, briefly igniting in fusion before dying again. Accretion disks around black holes will flare when they capture stray matter, producing violent flashes visible across light years. But these will be the exceptions, tiny sparks in a vast ocean of black. Millions of years could pass between such events, the intervals growing longer as the universe expands and matter thins. Over longer spans, black holes will gather the remaining matter. Stellar remnants, planets, asteroids, even drifting clouds of gas will fall into their gravity wells. Galaxies will become dominated by these invisible giants, each one a final archive of the mass that once formed stars. For eons beyond imagining, they will appear eternal, fixed monuments in a universe without change. Yet Hawking's prediction of black hole evaporation undermines even this apparent permanence. A stellar mass black hole will take 1067, 1067, 1067 years to evaporate through Hawking radiation. The supermassive black holes at galactic centers, millions or billions of times the sun's mass, could last up to 10100, 10100, 10100 years. But even these will eventually fade, radiating away their energy in a whisper of heat until nothing remains when the last black hole dies. The universe will have entered a new era, one in which all macroscopic structure is gone. This final chapter is almost beyond imagination. the cosmos will contain only subatomic particles, photons stretched into wavelengths longer than galaxies, and the faint relic heat of a universe gone cold. Entropy will be near its maximum. Without gradients of temperature or energy, no organized processes can occur. Time, in a physical sense, will have lost its arrow, for change itself will have nearly ceased. And yet, even here, quantum mechanics whispers of possibility. The vacuum is never truly empty. Virtual particles still flicker into and out of existence. In this sea of near nothing, rare fluctuations could, in theory, produce small islands of structure, even in some interpretations, entire new universes. The deeper science explored these far futures, the more it recognized a fragile truth. Our current vacuum may not be the lowest possible energy state. It could be metastable, a false vacuum, balanced precariously in a shallow valley of the cosmic energy landscape. If so, a quantum fluctuation or a high-energy event could trigger a phase transition to a true vacuum, one with lower energy and different physical laws. This change would propagate at the speed of light, rewriting the rules of reality in its path. Such an event could happen at any time or never. Nature has already endured extreme conditions in supernova, neutron star collisions, and black hole mergers without triggering it. But the possibility remains, hanging over the deep future like an unblinking star. Dark energy's nature adds another layer of uncertainty. Current observations suggest it is constant, a fixed energy density in space itself. But if it changes over time, the future could unfold in radically different ways. If dark energy grows stronger, the accelerating expansion could spiral into a big rip, tearing apart galaxies, stars, planets, and even atoms in the final seconds of the universe's life. If it weakens or reverses, the expansion could slow, stop, and reverse into a big crunch, collapsing all matter and energy back into a singular state, perhaps to ignite a new Big Bang. These possibilities remain speculative, but each is grounded in equations we already use to describe the cosmos. The uncertainty lies not in the math, but in the values nature has chosen for its constants. Values we can only measure, never dictate. It is difficult to convey the magnitude of these timescales. 1 billion years is already nearly impossible. To imagine the age of the universe itself is only 13.8 billion years. Yet the eras we speak of, the death of the last star, the evaporation of the last black hole, occur on timescales, trillions, quadrillions, and quintillions of times. Longer, on such scales, even the concept of event changes meaning. The collision of two black dwarfs becomes as rare as a supernova is today, but the pause between them lasts longer than the history of the cosmos so far. And yet, even in these unimaginable stretches, the universe is not frozen. It is simply patient. The path to a starless tomorrow is not only a tale of loss, but of transformation. The universe does not stop when the lights go out. It changes its language. From the warm glow of fusion to the cold pull of gravity, from the slow decay of matter to the faint heat of black hole evaporation. Each era is a verse in a poem written over incomprehensible eons, but whether that poem ends in silence or gives way to a new stanza, a rebirth in some altered form, remains the question that draws science onward. One alternative depends on the true nature of dark energy. Observations suggest it is constant, but if it grows stronger over time, its repulsive effect will increase. Galaxies, bound together by gravity, will be the first to fall apart. Then, Stars within galaxies will be torn from their orbits, planets stripped from stars. Eventually, the tidal force of expansion will overwhelm atomic bonds, ripping matter itself into a spray of fundamental particles. In this big rip scenario, the end comes not in the silence of heat death, but in a final, accelerating disassembly, a tearing of the universe's fabric at every scale. The time scale depends entirely on how fast dark energy's strength changes. It could be trillions of years away, or far sooner. If, on the other hand, dark energy is not constant but decreases with time, the universe's expansion could slow, stop, and reverse. Galaxies would begin to move toward one another, accelerating inward as gravity reclaimed its dominance. Eventually, all matter and energy would collapse into a single, dense point, a big crunch. From here, speculation widens. Could such a collapse trigger another Big Bang? Cyclic cosmologies imagine an eternal rhythm of expansion and contraction, a universe that dies and is reborn over and over, each iteration perhaps carrying subtle differences in its physical laws. In such a model, the starless tomorrow is not a final destination, but a transitional phase, a deep inhalation before the next cosmic breath. Beyond these grand dynamics of expansion and contraction lies an even stranger possibility: vacuum decay. In quantum field theory, our universe exists in a particular vacuum state, a configuration of fields with a certain energy. But there is no guarantee this state is the absolute lowest possible. If it is metastable, a false vacuum, then somewhere, sometime, a quantum fluctuation or extreme event could push a small region into a lower energy true vacuum. The result would be catastrophic. The laws of physics inside the new vacuum could be entirely different. The speed of light, the strength of forces, even the nature of matter itself could change. The boundary between the old and new vacuum would expand at the speed of light, rewriting reality as it went. There would be no warning. One instant, the universe as we know it; the next, gone. Although this scenario is permitted by theory, calculations suggest the probability is vanishingly small over the universe's current age. But on the time scales of trillions or quadrillions of years, vanishingly small becomes a lingering possibility. Quantum theory offers yet another speculative thread that fluctuations in the vacuum, given infinite time, could randomly produce pockets of low entropy. These might be small and fleeting, or vast enough to ignite entirely new universes. Some of these fluctuations might create so-called Boltzmann brains, self-aware observers emerging spontaneously from chaos, only to dissolve again. Others might spawn regions with matter, radiation, and the conditions for stars and galaxies. If this is possible, the heat death might not be the final word, but the backdrop for sporadic, unpredictable acts of creation. Our own Big Bang could have been one such fluctuation, blooming briefly into a long WLTO glimpse. The path ahead is one thing. To understand why it must be so is another. And here, in the deep future of the cosmos, science moves from the surety of observation to the layered territory of theory. The lights have not yet gone out, but their fate is written in equations that point toward multiple endings, each built upon the same physical laws that govern the present. The most widely accepted vision remains the heat death, the silent erasure of all structure as the universe approaches thermodynamic equilibrium. Here, entropy reaches its maximum. Energy is evenly spread across space, and no process can occur that creates usable work. The physics is brutally simple. The second law of thermodynamics is not a suggestion. It is a command. Stars, planets, and black holes can only delay, not prevent, the slow march toward uniformity. Once all gradients of temperature vanish, the cosmos becomes an eternal, unchanging sea of cold radiation and inert particles. But this vision is not the only one science entertains. For as complete as the heat death appears, there are loopholes in the laws we know, cracks through which other possibilities enter the universe before sinking back into equilibrium. Among more exotic astrophysical speculations is the idea of dark stars, objects powered not by fusion, but by dark matter annihilation. If certain forms of dark matter can self-annihilate, releasing energy, then under rare conditions, these particles could gather into dense clouds and radiate light for eons, after ordinary stars have gone out. While this would not prevent the starless, tomorrow it could punctuate it with rare points of light, scattered like distant lighthouses across a largely black sea. These dark stars would not be eternal, but they could delay the absolute darkness by trillions or even quadrillions of years. Some physicists and philosophers have asked whether a sufficiently advanced civilization could survive in a dying universe. Could it gather and store energy from the last stars? Could it harness black hole evaporation as a power source? Theoretical proposals suggest it might be possible to build structures that collect and conserve energy in ways that stretch subjective time for conscious beings, allowing them to experience a much longer final era than the universe would otherwise allow. This is speculative engineering on a cosmic scale, perhaps forever beyond reach, but it is one of the few visions that confronts the darkness with defiance rather than acceptance. Each of these scenarios, heat death, big rip, crunch, vacuum decay, quantum rebirth, flows from the same physics we use to understand the present. They differ not in the framework, but in the parameters, the strength and nature of dark energy, the stability of the vacuum, the ultimate behavior of matter under extreme conditions. For now, observation can narrow the range, but not yet choose the final answer. The instruments we build today, telescopes, particle colliders, gravitational wave detectors, may one day provide the missing pieces. But in the meantime, the far future remains a canvas of possibilities, each carrying its own form of beauty and terror. Theories can chart the roads ahead, but they cannot yet tell us which road the universe will take. And so we stand at a strange point in cosmic history. We know more about the fate of stars than any generation before, and yet the final act of the cosmos remains a mystery written in the uncertain language of the far future. What is certain is that whatever path is taken, the journey toward a starless tomorrow will shape not only the physics of the universe, but the meaning of time itself. The fate of the universe may lie trillions of years ahead, but the tools to probe it are being built now, in quiet mountaintop domes, deep underground chambers, and orbiting observatories. Instruments designed by human hands are reaching into the deep future, not by waiting for it to arrive, but by reading its faint signatures in the present. The challenge is immense. We cannot watch stars fade over millions of years, or see galaxies vanish beyond the cosmic horizon in a single lifetime. Instead, we must search for traces, evidence etched into the light of ancient stars, the faint glow of the early universe, the subtle drift of cosmic expansion. The James Webb Space Telescope, JWST, with its infrared eyes, is looking billions of years into the past, to the first galaxies born after the Big Bang, by charting how star formation rates have changed over cosmic history. astronomers can project those trends forward. Already, the data shows that the universe's star-making peak occurred billions of years ago. Since then, the rate has steadily declined. This decline is the first curve in the long descent toward the last star. Complementing Webb, the Nancy Grace Roman Space Telescope, set to launch in the coming years, will map the distribution of galaxies and measure the influence of dark energy with unprecedented precision. Understanding how dark energy behaves is key to predicting whether the cosmos will drift into a slow heat death, collapse in a big crunch, or tear itself apart in a big rip. On the ground, the Verisi-Rubin Observatory will scan the entire visible sky every few nights, tracking billions of stars and galaxies. It will reveal how stars age in real time and detect rare transient events, the flickers of supernova and stellar collisions that still punctuate the universe's slow decline. The night sky is not the only record. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, contains information about the universe's density, composition, and expansion rate. Experiments like Planck and the upcoming CMBs for Project measure its minute fluctuations with extraordinary precision, refining our understanding of how cosmic acceleration began and where it is heading. Beyond light, astronomers now listen to the universe in gravity, the Laser Interferometer Gravitational Wave Observatory LIGO and its partners detect ripples in space-time from massive collisions, black holes merging, neutron stars colliding. Over cosmic time, these events will become rarer, but their distribution today helps scientists model how quickly the universe's reservoirs of massive stars are being depleted. While telescopes look outward, some of the most important tests are taking place underground, far from cosmic light, in enormous tanks of ultra-pure water, such as those in Super Kamio Konde in Japan, and in massive liquid scintillator detectors like Juno in China. Physicists watch for the faint signs of proton decay. If protons, the building blocks of atoms, are unstable, then all ordinary matter will eventually vanish, even before the last black holes evaporate. To date, no proton has been seen to decay, setting a lower bound on its lifetime of at least 103 for years. But the search continues. Each year without detection pushes that lower bound higher, constraining the grand unified theories that predict decay. Direct observation cannot span the full timeline of the universe, but can simulate it. Programs running on the world's fastest machines, such as Illustristing and EAGLE, model the growth and aging of galaxies, the cooling of white dwarfs, and the dispersal of matter by gravitational encounters. These simulations incorporate the physics of dark matter, dark energy, stellar evolution, and cosmic expansion. By running them forward, scientists can watch galaxies fade, clusters dissolve, and black holes dominate, and then compare those predictions to present-day data. Every match between model and reality strengthens our confidence in the road. Mapped to the starless tomorrow, because the ultimate fate of the cosmos may hinge on the stability of the vacuum. Particle accelerators, like the Large Hadron Collider LHC at CERN, also play a role. By measuring the mass and interactions of the Higgs boson, physicists can test whether our vacuum is likely stable, metastable, or unstable over cosmic time. The results so far suggest a delicate balance, a vacuum that could persist for trillions of years, but that might also be susceptible to eventual decay. The uncertainties are large, and narrowing them will require both higher energy experiments and more precise theoretical calculations. High-precision atomic clocks now accurate to within a billionth of a second, are also being turned toward cosmic questions by comparing clocks in different locations and gravitational environments. Scientists can test whether the fundamental constants of nature, like the fine structure constant or the ratio of electron to proton mass, are truly constant over time. Any drift in these values could indicate that the vacuum's properties are changing, hinting at a future very different from the static heat death envisioned today. Some of the most ambitious projects are devoted to pinning down dark energies. Exact nature. The Euclid mission, launched by the European Space Agency, will map the large-scale structure of the universe with exquisite detail, revealing how cosmic expansion has changed over time. Combined with Roman surveys, it will allow scientists to test whether dark energy is constant, dynamic, or something stranger still. These measurements are critical because the smallest shift in dark energy's behavior can alter the universe's fate entirely, changing a slow fade into lightless heat death into a sudden big rip, or even a reversal into collapse. The tools themselves are only part of the story. Each observation, each measurement, becomes a thread in an ongoing conversation with the universe, one that spans not just the breadth of space, but the depth of time. We live in a moment when the night sky is still ablaze, when galaxies are still within reach, when the afterglow of the Big Bang still hums faintly across space. But the data being gathered now will allow future generations, perhaps thousands of years from now, to know how the cosmic story will end. The precision of these tools gives us something extraordinary, the ability to place ourselves on the timeline of the universe's life, to see where we stand between its fiery birth and its eventual silence. And with each new image, each new number, the outlines of the starless tomorrow grow sharper from here. Only one step remains, 2 steps back from the equations, the detectors and the simulations, and consider what such a future means, not only for the universe, but for those within it who can imagine its end. There will come a night when the sky no longer answers, a night when no constellation rises, when no soft glow breaks the horizon, when the silence between galaxies has swallowed even their names. That night will not arrive with violence, but with a long, patient fading, the slow retreat of starlight into history. We now know this not as prophecy, but as calculation. The equations have been tested, the trends observed, the patterns traced backward into the past and projected far forward into the dark. Stars are mortal, galaxies age, space itself drifts and stretches, pulling the light thin until even memory fades. From a human vantage point, these timescales are almost cruel. The life of a civilization, the span of a species, even the whole chapter of life on a planet is a blink compared to the ages between the first and last star. And yet, our minds are able to step beyond our moment, to picture the world without us, and the universe without worlds. This ability to imagine the starless tomorrow is perhaps our most mysterious inheritance from the cosmos. We are made of its atoms, bound by its laws, and yet we can look at it and see not only what is, but what will be in the dark future. There may be no eyes to watch the cooling of the last white dwarf, no instruments to measure the final whisper of a black hole's evaporation. And yet, that does not make the vision meaningless. To see it now, while the sky is still alive, is to understand the arc of all things: birth, change, decline, and transformation. The physics is indifferent. Entropy does not mourn. Expansion does not hesitate out of pity. But we, the fleeting arrangements of matter and energy that can reflect upon their own impermanence, do mourn. And in that mourning there is beauty. The starless tomorrow is not only an ending, it is a mirror. It shows that permanence was never the law of the universe, only the illusion of a limited perspective. Mountains erode, continents drift, stars exhaust themselves, and galaxies drift apart. The sky's apparent stillness is only the speed of change slowed beyond our senses. Ancient peoples once believed the stars to be eternal guardians, fixed in their constellations for all time. Today, we know they are travelers, each moving through its own story, each destined for silence, and this knowledge deepens rather than diminishes. Their wonder, there is another way to see the starless future, not as a void, but as a transformation. The matter that once burned in stars will not vanish. It will change form. Atoms may decay, but the fundamental energy they represent will disperse into the great, quiet fabric of space. In that sense, the universe will not end in nothingness, but in a kind of stillness, a state where no more change is possible. For some, that is the truest death. For others, it is a kind of peace. Speculation offers other endings, a big rip, tearing the cosmos apart. A big crunch collapsing it back into a seed. A quantum fluctuation igniting an entirely new universe. In each case, the starless tomorrow may be only a chapter break in an endless book. But even if such rebirth is possible, we cannot assume it. And perhaps that is why the image of the last star resonates so deeply. It may be the final moment in which the universe contains light as we know it. The last breath of the era we've belonged to. In the face of such a timeline, human concerns seem impossibly small, but scale is not the same as meaning. The brevity of a life does not strip it of significance. It gives it urgency. If the cosmos is moving toward a long night, then our day, this brief age of light, is all the more precious. Every star we see tonight is a reminder that we live in a rare moment in cosmic history, a moment when the sky is still rich with fire. We are the witnesses of a chapter that will not come again. The camera in the mind's eye drifts outward now, past the orbits of planets, past the edge of the solar system, into the deep between the stars. Here, the Milky Way stretches across the dark like a river of light, ancient, fragile, alive. Further still, other galaxies appear, each with its own millions of suns. They shine together for now, but the physics we have traced whispers that this is temporary. A brief and golden interval before the long, slow parting. Even further, the clusters and filaments of the cosmic web emerge, immense strands of light and matter suspended in expanding space. In this vast perspective, the human story is as small as a breath, but it is part of the story nonetheless. And then, as the view continues to recede, the light of the galaxies begins to dim. Time accelerates in the mind's vision. Stars age and vanish. Galaxies fade to faint red smudges, and then to black. Black holes rule for a time, then dissolve into invisibility. The scene grows quiet. At last, there is no light at all. Only the invisible shimmer of particles and the endless reach of space in the final image. The universe is neither tragic nor triumphant. It simply is. It has followed its laws to their conclusion. The lights have gone out, but the vastness remains. Voice rises softly over the darkness. We are not here to stop the night from falling. We are here to see it while the stars still burn, to know that they will go out, and to treasure their light all the more for it. The path to a starless tomorrow is already written, but so is this moment, this rare age of brilliance, and it is ours